Alright folks, in this video I want to go over relative extrema and absolute extrema. So extrema is just a fancy way of saying both min and max. I know in a previous video, namely the first derivative test, we went over how to find relative extrema, relative min, relative max. Here we're going to learn more so how to find the absolute min and max. Alright, so just a couple quick definitions and we'll get into some problems. So relative extrema, so once again, extrema mean both min and max, can occur over an open interval or a closed interval. Okay, so what's an open interval? So an open interval is something like this. Let's say we're going from negative infinity to positive infinity for the x values. That's what we call an open interval. So because that interval never stops, we can't have an absolute min and max. I'll explain that in a second. And as we discussed in previous videos, relative extrema can only occur within these valleys or peaks. If you're in a mountain valley, as I call it, you have a relative minimum. If you have a peak, you have a relative maximum. All right, let's talk about absolute extrema. So on the other hand, absolute extrema can only occur on closed intervals. So what that means is that we're chopping off our function at specific values. In particular, let's say the closed interval went from, let's say, -2 to 5. This is now a closed interval. Because the interval stops, because we actually get to -2 and 5, we're going to have an absolute min or max. The absolute max occurs at the highest part of the graph, which is the largest y value, and the absolute min occurs at the lowest part. And it turns out that absolute extrema do not have to be located in valleys or peaks. For relative extrema, we need valleys and peaks, but for absolute, we relax that restriction. We do not need a valley or peak to have an absolute min or max. And note that whether you're absolute min or max or relative min or max, local and absolute extrema must be finite, meaning you cannot have an absolute min or max of infinity or negative infinity. Okay, let's look at a couple of graphs here. For example, let's say we had a graph that looked like this. Okay, let's say our graph. Let's say it did something like this. Okay, let me give you a couple of ordered pairs here. Let's say this point right here. Let's say it's a 2, 4. These are ordered pairs. Right here, let's say the ordered pair is a 5, -1. Okay. All right. So the question here would be, what is the absolute minimum? Or let's take it back. What's the relative min? What's the relative min? Okay. Well, we have a relative minimum because we have a value that's located in a valley. And the relative minimum is located at x equals 5. So this is the location of the relative minimum. If we want to know the value of the relative minimum, the value is going to be what the y-coordinate is. In this case, it's a -1. So when you're doing your homework, make sure you understand, are they asking for the location or are they asking for the actual value? The location is the x-coordinate. The value itself is the y-coordinate. Okay, so we have a relative minimum. What about relative max? Yes, we're going to have a relative max. The location will be at x equals 2, because that's our peak there. And the value of the relative max is going to be 4. Once again, that's the y value. Okay. Now, do we have an absolute min? We do not. Why not? Because we're actually looking over an open interval. These arrows indicate that we're going up and to the right forever, we're going down and to the left forever. And remember, we said that absolute, any extrema, min, max, relative, absolute, it can't be infinite. So because this graph goes up forever, there's no absolute minimum. Because the graph goes down forever, there's also, because the graph goes down forever, there's no absolute minimum. Because the graph goes up forever, there's also not going to be an absolute max. Okay? So that one we only have relative extrema. We didn't have any absolute extrema. That's because this is an open interval. It just keeps going forever. Well, what if we had a function over a closed interval? Let me show you what that looks like. Suppose we had a graph that did something like this. All right. Once again, I'm going to fill in some ordered pairs for convenience here. Let's say this one right here is a 1, 2. Let's say this point up here is a 3, 6. Let's say this point down here is a, I don't know, 5, 1. And let's call this a 7, 4. Just making up some ordered pairs here. All right. So notice this particular graph is on a closed interval. In terms of x values, this function is contained between x values between 1 and 7. Okay? So we are now working with a closed interval, which means we will have an absolute min or max. And that's what your extreme value theorem is telling you. It's saying when you're on a closed interval, you absolutely will, pardon the pun, have an absolute min and an absolute max because the graph stops. All right, so let's go through the whole workup. So what is our relative minimum? Or do we have one? Yes, we have a relative min because we have a valley. And the relative min, the location is at x equals 5. The value of the minimum is equal to 1. Okay, I'm looking at that valley at the order pair 5, 1. Do we have a relative max? Yes, we do. We have a relative max at x equals 3. And the value of the absolute max is 6. Okay. Do we have an absolute max? We will because, as I just told you, the extreme value theorem tells you there will be a max because of the closed interval. So to figure out the absolute max, you have to ask yourself, all right, what is the absolute highest part of this graph? I don't care if it's in a valley or if it's in a peak or anything like that. I don't care. What's the highest part of this graph? Well, it turns out, this won't always be the case, but it turns out that that relative max at 3, 6, it also happens to be an absolute max. So we have an absolute max at the same location of the relative max. So the location's at x equals 3, value is equal to 6. And it also turns out that our absolute min is in the same location of the relative min. As I said, this is just by coincidence. It won't always be the case. So now our absolute min will be located here because this is now the lowest part of the graph. So our absolute min is at x equals 5. The value is equal to 1 there. Okay? All right, now what I want to do is let me make a quick little change so you guys can see what an absolute max is really saying here. So I'm going to go to the far right point here, the 7, 4. Let me get rid of that, and let's make that point go up a little higher. So let's say that point actually went all the way up to here. And now let's say this order pair is, let's say 7, 8. So now what happens to this graph now is that, well, we are going to have a new absolute max. Why is that? Because now we have a new overall highest point of the graph. So if instead this was the graph, I hope this is not confusing anybody. If this is the graph, then now the 7, 8 now becomes the ordered pair of the new absolute max. But keep in mind, that does not change the fact that 3, 6 is still a relative max. All right. So coming down here where we have absolute max for this new graph, we would have an absolute max at x equals 7, and the value of that absolute max is equal to 8. So an absolute min or max does not have to be contained within a valley or peak. All right, so once again, be careful in your homework when they ask you for what's the location versus what's the value. All right, let me show you how to do this whole absolute min and max stuff by hand. So what if instead of giving us a graph, they gave us a function? For example, suppose they told us f of x is equal to a negative 2x squared plus x minus 1, and they want us to find the absolute minimum value on the interval going from negative 2 to 4. Okay? All right, so here are the steps to find absolute min and max when you're given a function. First step, as any step that we've been doing recently, it seems like, first step is take the derivative. Okay. The second step is we're going to evaluate, which means plug in, we're going to evaluate f of x at the endpoints and critical values. Okay, if you remember from the first derivative test, our critical value is when we take our first derivative and it's where it's equal to 0. That's what we're going to do. Then the third step is you just eyeball it. So then now, because remember f of x is your y value, so your largest function value, so your largest y value, that corresponds to your absolute max. The smallest y value is then your absolute min. Okay. Let me go back to step 2 for a second. So why are we worrying about endpoints and critical values? Well, go back to the previous 2 examples we did. Sometimes our absolute max or min was contained at the endpoint. Sometimes it was at the critical value because that's where the relative min or max is going to be. So that's why we have to test both of those and see which one's the largest. Okay, so back to our particular question. Our first step here is to find the derivative. So f prime of x is equal to a negative 4x plus 1. All right, to find the critical value, we set that value equal to 0. Solve for x, I'm going to subtract 1. Negative 4x is a negative 1. Divide through by a negative 4. And we get that x is equal to a positive 1/4. This is our critical value. And then next, we need to take that critical value and our endpoints, and we need to plug them into the original function. But let me say this. Make sure you only use critical values that are within your specified interval. What do I mean by that? Remember, our interval goes from negative 2 to 4. So we are only concerned with x values between negative 2 and 4. If I get a critical value that's not within that region, I don't test it. Okay, so what I'm saying is we need to calculate f of negative 2. We need to do f of positive 4. All right, those are the endpoints. And then I'll also have to evaluate f of 1/4. So these will give me the y values for my endpoints and my critical value. Okay, so to do this, I'm going to go to our calculator, if it works. All right. And then I am simply going to, what's happening? I am going to go to the table in my calculator. Okay, so let me make sure my setup is okay. So I'm going to hit second window. I want my independent variable to be on ask. Okay, so then we're going to go to y equals, and we're going to type in our f of x, our original function, which, if you recall, it was a negative 2x squared plus x minus 1. Okay, so that's a negative 2x squared plus x. Subtract away 1. Okay, next we're going to go to our table, and we are going to plug in our endpoints, which were a negative 2, 4, and also our critical value, which was a negative 1/4. If I am correct, let me double check those values. Negative 2, 4, positive 1/4, positive 1/4. All right, so let's go back. Let's change that x value to a positive 1/4. Okay? So we get negative 11, negative 29, negative 0.875. Negative 0.875. Make sure I grab those correctly. Okay, all right. So now, once we have those function evaluations, we just simply look at them and we say, okay, for the absolute minimum, we're looking for the smallest y value. So remember, negatives are weird. So right here, let me do a different color. This gives us the location and the value of our absolute minimum because that's the smallest y value. So we want to know, the question says, what's the actual value of the absolute minimum? So the answer is negative 29. So negative 29 is our absolute minimum value. If they ask for what's the absolute max value, it's going to be the negative 0.875 because that's the largest y value. This will be our absolute max value. Okay? All right, folks. Hope this helps you out with your next homework. See you in the next video.